What if CERN isn't just probing reality, but unraveling it? For years, we've been told the Standard Model is the bedrock of particle physics. But recent data from the Large Hadron Collider suggests something doesn't quite add up. Measurements showed unexpected particle behavior. Scientists discovered anomalies that defy current explanations. The evidence shows a crack in the very foundation of our understanding. Is this a minor blip, or are we on the verge of a paradigm shift? The implications extend far beyond the physics lab. Are we prepared for what CERN might unleash? 95% of the Standard Model relies on assumptions we've never actually verified. It's a mathematical house of cards, and the LHC data might just be the breeze that brings it all down. For decades, the Standard Model has been particle physics' reigning champion. It neatly organizes all known fundamental particles and forces, except gravity, into a comprehensive framework. Quarks, leptons, bosons. They all have their place, their properties defined, their interactions meticulously charted. It's the theory we use to predict what happens when particles collide at near-light speed, and the theory that underpins much of modern physics. But what if the map isn't the territory? What if the elegance of the Standard Model is blinding us to a deeper, more complex reality? The LHC, with its unprecedented energy and precision, is designed to test the very limits of this model. Scientists smash protons together, recreating the conditions that existed fractions of a second after the Big Bang. They watch for new particles, for deviations from predicted behavior, for anything that might hint at what lies beyond the Standard Model. And that's where the anomalies come in. These aren't just minor discrepancies, statistical flukes that can be easily dismissed. The measurements showed muons behaving in ways that don't align with theoretical predictions, specifically the muon's magnetic dipole moment. Essentially, how strongly it interacts with a magnetic field is slightly off from what the Standard Model predicts. It's a tiny difference, but significant enough to send ripples through the physics community. Think of it like this. You're building a bridge, and every calculation says it should hold a certain weight. But then you test it, and it buckles slightly under less weight than expected. That small deviation could indicate a fundamental flaw in your design. The muon anomaly is similar. It suggests that there are particles or forces at play that the Standard Model doesn't account for. These unknown elements are subtly influencing the muon's behavior, pulling it away from the predicted path. This could be evidence of new particles interacting with muons. Maybe there are heavier versions of known particles or entirely new fundamental particles that we haven't discovered yet. It could also point to new forces beyond the four known forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These new forces might be mediated by new bosons, particles that carry the force. The problem is, the Standard Model has been so successful for so long that physicists have become comfortable with its predictions. It's become the default explanation for everything. Questioning it feels like questioning the foundations of physics itself. Furthermore, there's no single universally accepted explanation for these anomalies. Different theories have been proposed, each with its own set of particles and forces. Some involve supersymmetry, which postulates that every known particle has a heavier superpartner. Others invoke extra dimensions, curled up at scales too small for us to perceive directly. The analysis continued. While the muon anomaly is perhaps the most well-known, it's not the only one. There are hints of similar anomalies in the behavior of B mesons, particles containing bottom quarks. These anomalies suggest that leptons, electrons, muons, and taus might not interact with the fundamental forces in the way the Standard Model predicts. These particles are all supposed to be identical, just heavier versions of each other, but these measurements showed they might be interacting differently with other particles. If confirmed, these lepton universality violations could shake the Standard Model to its core. The implications extend to our understanding of dark matter. Dark matter accounts for about 85% of the matter in the universe, but we have no idea what it is. Some physicists believe that dark matter particles might interact with the known particles through new forces, explaining the observed anomalies. And then there's the problem of neutrino mass. Neutrinos are nearly massless particles that interact very weakly with matter. The Standard Model originally predicted that neutrinos should be massless, but experiments have shown that they do have a tiny mass. This discovery, which earned the 2015 Nobel Prize in Physics, already necessitates an extension of the Standard Model. Could the anomalies observed at the LHC be related to the mystery of neutrino mass? The deeper question is, are these anomalies a sign of something truly new, or are they simply the result of experimental uncertainties or theoretical approximations? Are we seeing a crack in the foundation or just a superficial flaw in the paint? It's crucial to emphasize that these are anomalies, not outright contradictions of the Standard Model. The Standard Model still accurately describes a vast range of phenomena. However, the anomalies suggest that it's incomplete, that there's more to the story than we currently understand. Scientists discovered that the Higgs boson, the particle responsible for giving mass to other particles, also poses problems. Its mass is much smaller than what theoretical calculations predict, leading to what's known as the hierarchy problem. Why is the Higgs boson so light compared to the Planck scale, the energy scale at which gravity becomes as strong as the other forces? Some physicists believe that new particles or forces are needed to stabilize the Higgs boson mass, potentially linking it to the LHC anomalies. Consider the implications if these anomalies hold up under further scrutiny. It would mean that our current understanding of the fundamental building blocks of the universe is fundamentally incomplete. It would open the door to new theories, new particles, and new forces, potentially revolutionizing our understanding of everything from the Big Bang to the nature of dark matter and dark energy. It's a daunting prospect, but also an incredibly exciting one. Where does that leave the Standard Model? Is it destined to be replaced by a more comprehensive theory, or can it be patched up to accommodate the new data? Neutrinos, those tiny, nearly massless particles that stream through everything. Ever wonder why they're so hard to pin down? They're often called the ghost particles of the universe, and for good reason. They interact so weakly with matter that they can pass through light years of lead without even noticing. But these elusive particles might just be holding the key to unlocking some of the universe's deepest secrets, and perhaps even explaining those LHC anomalies. Neutrinos come in 3 flavors: electron, muon, and tau. What's really weird is that they can oscillate between these flavors as they travel. This means a neutrino born as an electron neutrino can spontaneously transform into a muon neutrino, and then back again. This oscillation is only possible if neutrinos have mass, which, as we discussed, contradicts the original Standard Model. The analysis continued. One of the biggest experiments dedicated to studying neutrinos is the Ice Cube Neutrino Observatory located at the South Pole. It's essentially a cubic kilometer of ice instrumented with thousands of light sensors. When a neutrino interacts with the ice, it can produce a shower of secondary particles that emit light, which IceCube detects. By studying these events, scientists can learn about the properties of neutrinos and their origins. But here's what's wild. Some experiments, like the Mini-Boonay experiment at Fermilab, have observed anomalies in neutrino oscillations that don't quite fit with the Standard Model's predictions. Mini-Boonay saw more electron neutrinos than expected, hinting at the existence of a fourth, sterile neutrino that doesn't interact with the weak force. That's right, a neutrino that barely interacts with anything. Now, the idea of sterile neutrinos isn't new. Physicists have been theorizing about them for decades. But the Mini-Boonay results, along with some other anomalies from reactor neutrino experiments, have reignited the debate. Are these anomalies just statistical flukes, or are they a sign of something truly new? Measurements showed a possible deviation, but the margin of error is still significant. The implications extend beyond just particle physics. Because neutrinos are so abundant in the universe, they could potentially play a role in dark matter. Sterile neutrinos in particular are a candidate for warm dark matter, which could help explain the distribution of galaxies in the cosmos. It is thought that because they have mass, they could contribute to the overall mass of the universe. Neutrinos are also produced in nuclear reactions inside stars and during supernova explosions. Studying these neutrinos can give us a unique window into these extreme astrophysical events. For example, the Super Kamiokande detector in Japan famously detected neutrinos from supernova 1987A, providing valuable insights into the core collapse process. The data reveals the important function these tiny particles serve in the universe. The search for new physics in the neutrino sector is one of the most active areas of research in particle physics today. There are numerous experiments around the world, both planned and already running, that are trying to precisely measure neutrino properties and search for new phenomena. These include experiments like DUNE, Deep Underground Neutrino Experiment, in the United States and hyper-Kamiokande in Japan. Consider the possibility that the LHC anomalies and the neutrino anomalies are somehow connected. Perhaps there are new particles or forces that affect both the Higgs boson and neutrinos, providing a link between the two seemingly disparate puzzles. Further examination revealed a potential correlation, but more data is needed. It's also worth noting that the standard model doesn't explain why neutrinos have such tiny masses. The masses of the other fundamental particles, like quarks and leptons, are generated by the Higgs mechanism, but this mechanism doesn't naturally account for the smallness of neutrino masses. This has led to theories like the seesaw mechanism, which postulates the existence of very heavy, sterile neutrinos that could explain the lightness of the known neutrinos. Neutrino research requires incredibly sensitive detectors and sophisticated analysis techniques because these particles interact so rarely with matter. But the potential payoff is huge. If we can unravel the mysteries of neutrinos, we might just be able to solve some of the biggest puzzles in physics, and perhaps even uncover new laws of nature. Scientists discovered the neutrino oscillation, which suggests they are not as simple as we once thought. And then there's the question of whether neutrinos are their own antiparticles. This is known as the Majorana nature of neutrinos. If neutrinos are Majorana particles, it would have profound implications for our understanding of matter and antimatter, and could even explain why there is more matter than antimatter in the universe. Meanwhile, the standard model continues to face scrutiny from all angles. While it remains the most successful theory of particle physics to date, it's clear that it's not the whole story. The anomalies in neutrino physics, along with the LHC anomalies and other puzzles like dark matter and dark energy, suggest that there are new particles and forces waiting to be discovered. The exploration of neutrino properties could well be the key to unlocking these secrets. This one kept me up way too late last night. It's about something called the muon G2 anomaly, and it's a mouthful, I know. But stick with me because it could mean the standard model, as robust as it is, has a serious crack in its foundation. So, what's a muon? Think of it as a heavier, unstable cousin of the electron. It's a fundamental particle, meaning it's not made up of anything smaller. And just like electrons, muons have a property called spin, which makes them act like tiny magnets. Now, here's where it gets weird. When you put a muon in a magnetic field, its spin axis starts to wobble like a spinning top that's starting to slow down. This wobble is called precession, and the rate at which it precesses is described by something called the G-factor. The standard model predicts the value of this G-factor with incredible precision. It's one of the most accurate predictions in all of physics, but when scientists actually measured the G-factor of muons, they found a tiny but significant discrepancy. It wobbles just a little bit faster than the standard model says it should. This difference is tiny. We're talking about a deviation in the 10th decimal place. But in the world of particle physics, that's like shouting from the rooftops. That level of precision matters. The first hints of this anomaly came from experiments at Brookhaven National Laboratory back in the early 2000s, but the results weren't quite conclusive enough to claim a discovery. So, a new, much more powerful experiment was designed and built at Fermilab near Chicago. The Fermilab experiment, called muon G2, started taking data in 2018, and in 2021 they released their first results. The results confirmed the Brookhaven anomaly with even greater precision. The combined results from both experiments now show a deviation from the standard model prediction at a level of 4.2 sigma. Now, in particle physics, we usually require a 5 sigma level of significance to claim a discovery. So 4.2 sigma isn't quite there yet, but it's very close. And it's enough to make physicists sit up and take notice. So, what could be causing this anomaly? Well, one possibility is that there are new particles or forces that we don't yet know about, interacting with the muons and affecting their wobble. These new particles could be virtual particles, popping in and out of existence in the quantum foam and subtly influencing the muon's behavior. It's like, imagine you're trying to predict the path of a bowling ball. You can calculate its trajectory based on its initial velocity and the angle you threw it. But what if tiny gusts of wind, imperceptible to the naked eye, were subtly nudging the ball off course? You might still get close to the right answer, but you'd always be slightly off. That's kind of what's happening with the muon G-factor. The standard model accounts for all the known particles and forces, but there could be unknown gusts of wind, new particles or forces, that are subtly affecting the muon's wobble. What's fascinating is that this muon G2 anomaly seems to line up with other hints of new physics that we've seen in recent years. For example, there are some anomalies in the decay of B mesons, which are particles containing a bottom quark. These anomalies suggest that leptons, which include electrons, muons, and taus, might not be behaving quite as the standard model predicts. And then there's the persistent problem of dark matter. We know that dark matter makes up about 85% of the matter in the universe, but we have no idea what it is. It could be that the new particles that are affecting the muon G factor are also related to dark matter. The implications extend far beyond just tweaking the standard model. If confirmed, it would open the door to a whole new realm of physics, with new particles, new forces, and potentially a whole new understanding of the universe. We're talking about a fundamental shift in our understanding of reality. The muon G2 experiment is still running, and they are continuing to collect more data. With more data, they can reduce the uncertainty in their measurements and hopefully reach that 5 sigma threshold for a discovery. And of course, other experiments around the world are also searching for these new particles and forces. December 2018. A team at Durham University published a paper that sent ripples through the astrophysics community. It wasn't a flashy announcement or a press conference, just a quietly released study with a stark conclusion. Our understanding of how dark matter shapes galaxies might be fundamentally flawed. The prevailing theory, called lambda CDM, paints a picture of dark matter as cold, collisionless particles that clump together under the influence of gravity. These clumps, or halos, then act as gravitational wells, drawing in ordinary matter, gas and dust, that eventually forms stars and galaxies. In this model, every galaxy sits within a vast halo of dark matter, like a ship anchored in a deep, invisible ocean. But the Durham team's simulations, which were some of the most detailed ever created, revealed a problem. The lambda CDM model predicts that there should be hundreds, even thousands of smaller dark matter halos orbiting within the larger halo of a galaxy like our Milky Way. These smaller halos should each host a dwarf galaxy, a small, faint collection of stars. The problem? We don't see them. We've only observed a few dozen dwarf galaxies orbiting the Milky Way, far fewer than the hundreds predicted by the lambda CDM model. This discrepancy, known as the missing satellites problem, has been a thorn in the side of cosmologists for decades. Now you might think, okay, so maybe the dwarf galaxies are just too faint to see. And that's a valid point. Dwarf galaxies are notoriously difficult to detect, especially the ones that are farther away or embedded in the glare of the Milky Way. However, the Durham team's simulations accounted for this. They predicted not just the number of dwarf galaxies, but also their size, brightness, and distribution. And even when accounting for observational limitations, the discrepancy remained. There simply aren't enough dwarf galaxies to match the predictions of the lambda CDM model. So what's going on? One possibility is that our understanding of how galaxies form within dark matter halos is incomplete. Maybe the process of star formation is less efficient in smaller halos, resulting in dwarf galaxies that are too faint to be detected. Or perhaps some of the dwarf galaxies have been disrupted or destroyed by tidal forces from the Milky Way. But there's another, more radical possibility, that our understanding of dark matter itself is wrong. The lambda CDM model assumes that dark matter particles are cold and collisionless. But what if they're not? What if dark matter particles interact with each other or with ordinary matter in ways that we don't yet understand? For example, some theories propose that dark matter particles can self-interact, meaning they can collide with each other and exchange energy. These interactions could smooth out the distribution of dark matter in small halos, making them less dense and less effective at attracting ordinary matter. This could explain why we don't see as many dwarf galaxies as predicted. Other theories suggest that dark matter particles can decay or annihilate, producing standard model particles like neutrinos or photons. These decay products could then interact with ordinary matter, heating up the gas in small halos, and preventing it from forming stars. These are just a few of the possibilities. The truth is, we simply don't know what dark matter is, or how it interacts with the rest of the universe. And until we do, we'll continue to be plagued by problems like the missing satellites problem. The implications extend beyond just counting dwarf galaxies. the distribution of dark matter also affects the rotation curves of galaxies, the speed at which stars orbit around the galactic center. According to Newtonian physics, stars farther from the center should orbit slower, like planets in our solar system. But observations show that the rotation curves of galaxies are flat, meaning that stars at the edge orbit at the same speed as stars closer in. This is one of the key pieces of evidence for the existence of dark matter. The extra gravity from the dark matter halo is needed to explain the flat rotation curves. However, the lambda CDM model predicts that the dark matter halo should be more concentrated towards the center of the galaxy, leading to a cuspy rotation curve. But some observations suggest that the rotation curves of dwarf galaxies are chord, meaning that the dark matter is less concentrated in the center. This discrepancy, known as the core cusp problem, is another challenge to the lambda CDM model. It suggests that dark matter may not be as cold and collisionless as we thought, and that it may interact with ordinary matter in a more complex way. So, where does this leave us? We have a model of the universe that works remarkably well on large scales. It accurately predicts the expansion rate of the universe, the abundance of light elements, and the distribution of galaxies on large scales. But when we zoom into the scale of individual galaxies, we start to see cracks in the foundation. The missing satellites problem and the core cusp problem are just two examples of these cracks. They suggest that our understanding of dark matter and how it shapes galaxies is incomplete. This doesn't mean that the lambda CDM model is completely wrong. It just means that it's not the whole story. There's likely some additional physics that we're missing, some new ingredient that needs to be added to the recipe. What could that ingredient be? More data might reveal the answer. Everyone assumed that the universe played by a certain set of rules, a cosmic instruction manual carefully followed since the Big Bang. But what if the universe isn't quite so obedient? What if there are hidden pages in that manual, pages we haven't even begun to decipher? CERN, the European Organization for Nuclear Research, isn't just about smashing particles together. It's about probing the very fabric of reality, about searching for those hidden pages. Their experiments aren't just confirming existing theories, they're designed to find the points where those theories break down, where the universe deviates from our expectations. They're looking for the cracks. And one of the most intriguing avenues they're exploring is the possibility of extra dimensions. Now, I know what you might be thinking. Extra dimensions? Sounds like science fiction. And yeah, it does. But the math behind it is compelling, and it could potentially solve some of the biggest mysteries in physics, including the hierarchy problem. Consider gravity. It's by far the weakest of the four fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. A simple magnet can overcome the gravitational pull of the entire Earth to pick up a paperclip. Why is gravity so weak? One potential explanation is that gravity isn't actually weak at all. It just appears that way to us because it's leaking into other dimensions. Imagine a water hose. If the hose has a tiny pinhole, the water will leak out, reducing the water pressure at the nozzle. Similarly, if gravity can propagate into extra dimensions, its strength would be diluted in our three-dimensional space. This is where CERN comes in. The Large Hadron Collider, LHC, is designed to create conditions similar to those that existed fractions of a second after the Big Bang. In these high-energy collisions, particles can be created that are heavy enough to interact with these extra dimensions. If these extra dimensions exist, some of the energy from the collisions might disappear, carried away by particles that escape into these hidden realms. Scientists at CERN are meticulously analyzing the data from the LHC, looking for these missing energy events. It's like searching for a phantom limb, something that's not there but whose absence tells you something profound. The search for extra dimensions is not just a theoretical exercise. It has the potential to revolutionize our understanding of the universe. If we could confirm the existence of extra dimensions, it would open up a whole new realm of possibilities. It could explain the nature of dark matter, the origin of the universe, and even the possibility of time travel. But how would we see these extra dimensions? They're not like the three spatial dimensions we're familiar with. We can move freely in those. Instead, these extra dimensions are thought to be curled up at incredibly small scales, far too small to be seen directly. It's kind of like an ant walking on a tightrope. To us, the tightrope is a one-dimensional object, a line. But to the ant, The tightrope also has a circumference, a tiny circular dimension that it can move around. Similarly, our universe might have extra dimensions that are curled up at the Planck scale, the smallest possible unit of length. The particles that travel into these extra dimensions wouldn't be ordinary particles. They would likely be exotic, heavy particles that interact only weakly with ordinary matter. These particles could be candidates for dark matter, the mysterious substance that makes up the bulk of the universe's mass. CERN's experiments are also looking for other signatures of extra dimensions, such as the production of tiny black holes. According to some theories, if extra dimensions exist, the force of gravity would be much stronger at very small distances. This could allow the LHC to create microscopic black holes, which would then quickly evaporate, releasing a burst of energy. The search for extra dimensions is a long shot, but the potential payoff is enormous. It could fundamentally alter our understanding of the cosmos, revealing a universe far stranger and more complex than we ever imagined. It's a testament to human curiosity, our insatiable desire to unravel the mysteries of existence. Whether they find them or not, the pursuit itself pushes the boundaries of knowledge and inspires us to think beyond the confines of our everyday experience. The data, of course, will ultimately speak for itself. And then there's the question of supersymmetry. There's a persistent problem in the data coming from the LHC. It's not a glaring headline-grabbing issue, but a series of subtle anomalies that keep popping up in various experiments. Individually, they might be dismissed as statistical flukes or experimental errors, but taken together they hint at something else. Something that our current models of particle physics can't quite explain. Think of it like this. Imagine you're trying to assemble a complex puzzle. You have a pretty good idea of what the final picture should look like, and most of the pieces fit together nicely. But then you notice a few pieces that just don't seem to belong. They're the wrong color, the wrong shape, or they have strange markings that don't match anything else in the puzzle. That's kind of where we are with the LHC data. We have a well-established theoretical framework, the Standard Model of Particle Physics, which describes the fundamental particles and forces of nature. It's been incredibly successful in explaining a wide range of experimental results. But these little anomalies are like those mismatched puzzle pieces, suggesting that there's something missing from our understanding. One of the most intriguing anomalies involves the decay of B mesons. B mesons are subatomic particles that contain a bottom quark. According to the Standard Model, these mesons should decay into different particles at predictable rates. But experiments at the LHC have found that some of these decays are happening at slightly different rates than expected. Specifically, B mesons seem to be decaying into muons and electrons at different rates, even though the Standard Model predicts they should decay at roughly the same rate. This is known as lepton flavor universality violation, and it's a big deal because it could point to the existence of new particles or forces that are interacting with muons and electrons differently. Another anomaly involves the muon's magnetic moment. The muon, like the electron, has a tiny magnetic field associated with it. The strength of this magnetic field can be calculated with great precision using the Standard Model. However, experiments have found that the muon's magnetic moment is slightly larger than predicted. This discrepancy could also be a sign of new physics beyond the Standard Model. So what could be causing these anomalies? Well, there are a number of possibilities. One is that there are new undiscovered particles interacting with the known particles in ways we don't yet understand. These particles could be mediating new forces, or they could be affecting the properties of the known particles in subtle ways. Another possibility is that the anomalies are related to the existence of dark matter. As we discussed, dark matter is a mysterious substance that makes up the bulk of the universe's mass. We don't know what it's made of, but it's possible that it interacts with ordinary matter through new, undiscovered forces. These forces could be responsible for the anomalies seen at the LHC. It's also possible that the anomalies are related to the existence of extra dimensions. As we discussed, some theories predict that our universe has more than 3 spatial dimensions. These extra dimensions are thought to be curled up at incredibly small scales, but they could still have an effect on the behavior of particles at the LHC. The LHC experiments are continuing to collect data and refine their measurements. As they do so, they'll be able to test these different possibilities and hopefully shed light on the origin of these anomalies. Here's what's wild. It's also important to keep in mind that these anomalies could simply be statistical flukes, Particle physics experiments deal with incredibly small particles and incredibly high energies, which means that there's always a chance of random fluctuations in the data. It's possible that these anomalies will disappear as more data is collected. However, the fact that these anomalies have persisted for several years and that they've been seen in multiple experiments suggests that they might be more than just random fluctuations. They could be a genuine signal of new physics, a crack in the standard model that could lead to a deeper understanding of the universe. The scientific community is split. Some researchers are incredibly excited, seeing these anomalies as a potential path to groundbreaking discoveries. Others are more cautious, emphasizing the need for more data and more rigorous analysis. Regardless, the existence of these anomalies highlights the importance of continued exploration at the LHC. The LHC is the most powerful particle accelerator in the world, and it's our best hope for uncovering the secrets of the universe. Even if these anomalies ultimately turn out to be nothing, the search for new physics will continue. And then, there's the question of what these anomalies could tell us about the very nature of reality. Are we on the verge of a paradigm shift, a moment where our understanding of the universe is fundamentally changed, or are these just temporary bumps in the road, destined to be explained away by refinements to the standard model? Only time and more data will tell, but it's the possibility of the former that keeps scientists pushing the boundaries of what's possible. The implications extend far beyond the subatomic world. Nobody saw this coming. Einstein himself famously called it spooky action at a distance. We're talking about quantum entanglement. At its core, quantum entanglement describes a situation where two or more particles become linked in such a way that they share the same fate, no matter how far apart they are. Measure a property of one particle and you instantly know the corresponding property of the other, even if they're light years away. It's as if they're communicating faster than light, which, according to Einstein's theory of relativity, shouldn't be possible. Consider two entangled photons. These photons are linked such that their polarizations are correlated. If you measure one photon to be vertically polarized, you instantly know the other photon is horizontally polarized, and vice versa. This happens instantaneously, regardless of the distance separating them. The weirdness here is that prior to measurement, neither photon has a definite polarization. They exist in a superposition of states, meaning they're simultaneously both vertically and horizontally polarized until the moment of measurement. The act of measuring one photon forces it to choose a polarization, and its entangled partner instantly mirrors that choice. This isn't just theoretical. Quantum entanglement has been experimentally verified countless times. Alan Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics in 2022 for their experiments with entangled photons, establishing the violation of Bell inequalities and paving the way for quantum technologies. Their work definitively showed that quantum entanglement is a real phenomenon, not just a quirk of quantum mechanics. But what does it all mean? The implications of quantum entanglement are profound. It challenges our classical understanding of space and time, suggesting that there might be a deeper, non-local reality underlying the universe. It raises questions about the nature of measurement and observation, and whether the act of observing something can fundamentally alter its state. Now, some interpretations of quantum mechanics, like the many worlds interpretation, attempt to explain entanglement by suggesting that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different possible outcome. In this view, when you measure one entangled particle, you're simply becoming entangled with a particular branch of the multiverse, where that particle has a specific property. Others, like the pilot wave theory, propose that particles are guided by hidden variables that determine their behavior, even when they're entangled. These hidden variables would allow for instantaneous correlations between particles without violating the speed of light. Of course, these interpretations are still debated, and there's no consensus on which one, if any, accurately describes reality. But the fact that such mind-bending ideas are even being considered highlights the radical nature of quantum entanglement. Furthermore, quantum entanglement is not just a philosophical curiosity. It has practical applications in quantum computing, quantum cryptography, and quantum teleportation. Quantum computers could use entanglement to perform calculations that are impossible for classical computers. Quantum cryptography uses entanglement to create secure communication channels that are impervious to eavesdropping. And quantum teleportation, while not teleporting matter in the science fiction sense, can transfer the quantum state of one particle to another, enabling the transmission of information without physically moving the particle itself. So, how does this relate to the anomalies observed at the LHC? Well, some physicists speculate that these anomalies could be a sign of new physics that goes beyond the standard model, potentially involving new particles or forces that mediate quantum entanglement in unexpected ways. Perhaps the anomalies are a hint that our understanding of entanglement is incomplete, and that there are deeper connections between entangled particles and the structure of space-time itself. Imagine, for example, that entangled particles are not just linked through space, but also through higher dimensions that we can't directly observe. These higher dimensional connections could allow for instantaneous correlations that appear to violate the laws of physics as we currently understand them. Or consider the possibility that the anomalies are a sign of a breakdown in the principle of locality, which states that an object is only directly influenced by its immediate surroundings. If locality is violated, then entangled particles could be influenced by each other regardless of the distance between them, potentially leading to unexpected interactions and particle decays at the LHC. These are just speculations, of course, but they illustrate the potential for quantum entanglement to play a role in the mysteries of the universe. The LHC anomalies could be a window into a deeper reality where entanglement is not just a quirky phenomenon, but a fundamental aspect of the fabric of space-time. The analysis continued. If gravity seems ridiculously weak compared to the other fundamental forces, it's not your imagination. It's a real problem, and it's called the hierarchy problem. Consider this. A simple refrigerator magnet can overcome the entire Earth's gravitational pull to stick to your fridge. That illustrates just how incredibly feeble gravity is. The electromagnetic force holding that magnet to the fridge is vastly stronger. And the strong and weak nuclear forces? They make gravity look like a complete joke. So the question is, why? Why is gravity so much weaker than the other forces? The standard model doesn't offer a satisfying explanation. It predicts that the Higgs boson, responsible for giving particles mass, should receive huge quantum corrections to its mass. These corrections would come from interactions with other particles, and they would be so large that they would push the Higgs mass up to the Planck scale, an energy level associated with quantum gravity where our current understanding of physics breaks down. If the Higgs mass were at the Planck scale, then all the forces would be unified, and gravity would be just as strong as the others. But the Higgs boson's mass is actually quite small, only about 125 giga-electronvolts. Giga-electronvolts. This is way, way below the Planck scale. It's like expecting a pebble to weigh as much as a planet. To keep the Higgs mass at its observed value, physicists have to fine-tune the parameters of the standard model to an absurd degree. It's like adjusting a million knobs simultaneously to get a single desired outcome. This level of fine-tuning seems unnatural and suggests that there's something missing from our understanding. One possible explanation involves supersymmetry, SUSY. Supersymmetry proposes that every particle in the standard model has a superpartner with slightly different properties. These superpartners would contribute quantum corrections to the Higgs mass that cancel out the large corrections from the standard model particles, keeping the Higgs mass at a reasonable value. However, the LHC hasn't found any evidence of superpartners at the energy levels that many physicists expected. This puts pressure on the supersymmetry explanation, although it doesn't rule it out entirely. It could be that superpartners are simply too massive for the LHC to detect. Another possibility involves extrasar dimensions. The idea is that gravity might not actually be weak. Instead, it could be diluted by spreading out into extraspatial dimensions that we can't directly observe. In this scenario, the other forces would be confined to our three-dimensional brain, while gravity would be free to propagate into the higher dimensional bulk. This would make gravity appear weaker to us than it actually is. There are different models of extra dimensions. One is the Randall-Sundrum model, which proposes a warped extra dimension where gravity is concentrated near a Planck brain and diluted as it propagates towards our TeV brain. This could explain why gravity is so weak at the energy scales we probe in particle physics experiments. Another intriguing idea involves the anthropic principle. This principle suggests that the universe's fundamental constants, including the strength of gravity, must be within a certain range to allow for the existence of life. If gravity were much stronger, stars would burn out too quickly and life wouldn't have time to evolve. If gravity were much weaker, galaxies and stars wouldn't form at all. Therefore, the observed weakness of gravity could simply be a consequence of the fact that we exist to observe it. While the anthropic principle can't be ruled out, many physicists find it unsatisfying because it doesn't provide a deeper explanation for why gravity is weak. It's more of an observation than a theory. The hierarchy problem remains one of the biggest mysteries in fundamental physics. It suggests that there is new physics beyond the standard model waiting to be discovered. The LHC anomalies, if confirmed, could provide clues to the nature of this new physics and help us understand why gravity is so weak. Scientists discovered that if the LHC anomalies are a hint of extra dimensions, the structure of space-time might be radically different than we currently imagine. You've been told string theory is just math, divorced from reality, that it can't be tested. It's a beautiful idea, but many physicists see it as a dead end because it hasn't made any testable predictions. But what if that's not entirely true? String theory, at its core, attempts to reconcile general relativity with quantum mechanics. It replaces point-like particles with tiny vibrating strings. The different vibrational modes of these strings correspond to different particles, and this framework requires extra dimensions of space-time beyond the three we experience directly. Now, one of the most intriguing implications of string theory is the possibility of a multiverse. The math suggests our universe might not be the only one. Instead, there could be a vast landscape of universes, each with its own set of physical laws and constants. The idea stems from the concept of the string landscape. In string theory, the extra dimensions are curled up into tiny, complex shapes called Calabi-Yau manifolds. There are an estimated 10 to the power of 500 different ways these extra dimensions can be compactified, each corresponding to a different vacuum state with different physical properties. Think of it like a vast energy landscape with countless valleys. Each valley represents a possible universe with its own unique set of physical laws. Our universe would then be just one particular valley in this landscape. This multiverse concept offers a potential solution to the hierarchy problem, that nagging question of why gravity is so weak compared to the other fundamental forces. In a multiverse, the physical constants, including the strength of gravity, could be different in each universe. Most universes would not be hospitable to life. They might have gravity that's too strong, causing stars to burn out too quickly, or gravity that's too weak, preventing galaxies from forming. Our universe, with its seemingly fine-tuned constants, would then be a rare exception, a place where the conditions are just right for life to emerge. It's not that our universe was specifically designed for us. It's more that we could only exist in a universe with these particular properties. It's a controversial idea, no doubt. It relies on the anthropic principle, which, as we discussed, many physicists find unsatisfying. But it does offer a potential explanation for the weakness of gravity without requiring new physics at the TeV scale, which is the energy range that the LHC is designed to probe. If the LHC anomalies are indeed a sign of extra dimensions, then the string theory landscape might be more than just a theoretical construct. It could be a glimpse into the reality of a multiverse. But how could we ever test the existence of other universes? It seems impossible, right? Well, some physicists have proposed that collisions between our universe and other universes could leave observable signatures in the cosmic microwave background, the afterglow of the Big Bang. These signatures would be subtle but potentially detectable with future experiments. The implications extend beyond just the hierarchy problem. The multiverse could also explain other mysteries, such as the value of the cosmological constant, which determines the expansion rate of the universe. The observed value of the cosmological constant is incredibly small, much smaller than theoretical predictions. In a multiverse, this small value could simply be a result of anthropic selection. Moreover, if the LHC anomalies are a sign of something even stranger, then we have to consider the possibility that the structure of the universe itself is not uniform. Imagine that our universe is not alone, but there are other universes next door. Now, imagine these universes exert a gravitational pull on ours. This could explain dark matter and dark energy, those mysterious forces that make up 95% of the universe. And then, consider what that implies about the very nature of reality. If our universe is just one bubble in a frothing sea of other, Universes, each with its own laws and constants, what does that say about the fundamental nature of existence? Is there a deeper reality that underlies all these universes? Or is each universe a self-contained entity, forever separate from the others? Here's what's wild. The LHC anomalies, if they hold up, could be a key to unlocking these profound questions. They could be the first experimental evidence that our universe is not alone, that we are part of a much larger, more complex reality than we ever imagined. Our universe might be fundamentally unstable. That's the terrifying implication of some of the data coming out of CERN. It all comes down to something called vacuum decay, and it's not pretty. Let's examine the concept. In physics, a vacuum isn't just empty space. It's the lowest energy state of a system. Think of it like a ball sitting at the bottom of a valley. It's stable. It's not going anywhere unless you give it a push. But what if that valley isn't actually the lowest point? What if there's an even deeper valley hidden somewhere? Our ball might be sitting in what's called a false vacuum. It seems stable, but it's actually just metastable. Given enough energy, or even just a random quantum fluctuation, the ball could tunnel through the barrier and roll down into the true vacuum. Now, translate that to the universe. Our universe might be in a false vacuum state. And if that's the case, then at any moment, a bubble of true vacuum could spontaneously appear. Inside this bubble, the laws of physics would be different. The fundamental constants, like the speed of light or the strength of gravity, could have different values. And that, to put it mildly, would be catastrophic. Imagine a bubble of true vacuum expanding outwards at nearly the speed of light. Everything it touches would be instantly rewritten according to the new laws of physics. Atoms would be torn apart, matter would be converted into something unrecognizable, and life as we know it would cease to exist. The implications extend beyond just theoretical musings. If the Higgs boson's mass and the top quark's mass are both within a certain range, it suggests our universe is indeed metastable. The data reveals that we're precariously close to the edge. Here's what's wild. Some scientists believe the LHC, in its search for new particles and forces, might inadvertently trigger a vacuum decay event. It's a long shot, granted. The energy required to create a bubble of true vacuum is likely far beyond anything we can achieve with current technology. But consider this. If the LHC anomalies are pointing towards new physics beyond the standard model, they could also be hinting at a landscape where the energy barrier separating our false vacuum from the true vacuum is lower than we think. And then, what protects us? Well, there's a good argument to be made that the sheer size of the universe is a defense. A vacuum decay event is most likely to originate from a quantum fluctuation. The bigger the volume of space, the more opportunities there are for that fluctuation to occur. But even with an enormous universe, the probability isn't zero. This means the very act of probing the fundamental laws of physics carries a tiny, almost immeasurable risk. We're essentially poking at the fabric of reality, and there's always a chance we might accidentally tear it. Scientists discovered a fascinating detail: the shape of the potential energy landscape. The valley our universe sits in is exquisitely sensitive to the mass of the Higgs boson and the top quark. Tiny variations in those masses can dramatically alter the stability of the vacuum. The analysis continued, and it yielded a startling conclusion. We're not just near the edge of stability, we're right on the knife's edge. A slightly heavier Higgs boson, or a slightly lighter top quark, and our universe would be firmly in the stable zone. A slightly lighter Higgs boson, or a slightly heavier top quark, and we'd already be gone. And then there's the question of what lies beyond the bubble of true vacuum. Is it just a void, a region of nothingness where the laws of physics are meaningless? Or is it something even stranger, a gateway to another universe with entirely different properties? This means we're not just talking about the end of our universe. We're talking about the potential creation of a new universe, born from the ashes of our own. It's a cosmic recycling process on a scale that's almost impossible to comprehend. The possibility of vacuum decay highlights the inherent fragility of existence. It's a reminder that the universe, for all its apparent grandeur and stability, is ultimately a delicate house of cards, teetering on the brink of oblivion. Meanwhile, scientists continue to refine their models, searching for any clues that might shed light on the true nature of the vacuum and the likelihood of a decay event. They're pushing the boundaries of our knowledge, venturing into uncharted territory where the stakes are higher than ever before. Here's what's wild. We're using the very tools that could potentially trigger our demise to understand the nature of that threat. It's a paradox, a cosmic catch-22 that underscores the inherent risks of scientific exploration. It's like disarming a bomb while simultaneously trying to figure out how it works. The implications extend beyond just the scientific realm. It touches on fundamental philosophical questions about our place in the universe and the meaning of existence. If our universe is destined to end in a cataclysmic vacuum decay, what does that say about our purpose? And then, we have to consider the possibility that this has happened before, that our universe is just one in a long line of universes, each born from the destruction of its predecessor. It's a sobering thought, but it's one that we can't afford to ignore. It's a cycle of cosmic birth, death, and rebirth on an unimaginable scale. The data reveals a universe balanced on a razor's edge, 99.999999999% vacuum stability. That's what the standard model tells us. So why are so many physicists losing sleep? Because that tiny, insignificant fraction represents the potential for everything to end. We've been circling around this concept of vacuum decay, but let's really dig into what it would mean to reimagine the cosmos in its wake, because it's not just about our universe disappearing, it's about what replaces it. Consider the implications. If a true vacuum bubble were to nucleate, expand, and consume everything, the fundamental constants of physics inside that bubble could be completely different. Gravity could be stronger or weaker. The electromagnetic force could operate differently. Even the masses of elementary particles like electrons and quarks could be radically altered. This isn't just a subtle tweak. We're talking about a universe where atoms might not even be stable, where stars might never form, where the very fabric of reality is woven with entirely different threads. Think about it. Our universe is finely tuned for life. The constants of physics are just right to allow for the formation of stars, galaxies, planets, and ultimately, ourselves. If even one of those constants was slightly different, the universe would be a barren wasteland, devoid of any complexity. Now, imagine a universe born from vacuum decay. A universe where the constants are wildly different. What would it look like? What kinds of structures could form? Could life even exist? It's almost impossible to say. We're limited by our own understanding of physics, which is based on the conditions in our universe. Trying to extrapolate that knowledge to a universe with completely different laws is like trying to understand the ocean by only looking at a puddle. Yet, the very possibility forces us to confront our own cosmic biases. We tend to assume that our universe is somehow special, that the laws of physics are the way they have to be. But vacuum decay suggests that this might not be the case, that our universe is just one possibility among an infinite number of others, each with its own unique set of rules. The implications extend beyond just the realm of physics. It touches on fundamental questions about the nature of reality itself. Is there a deeper, more fundamental level of reality that underlies all of these different universes? A set of laws that governs the constants of physics themselves? Some physicists believe that the answer might lie in string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. The different vibrational modes of these strings would correspond to different particles and forces, and the constants of physics would be determined by the geometry of the extra dimensions that are curled up at the Planck scale. In this picture, vacuum decay could be seen as a transition from one stable configuration of strings to another, a shift in the geometry of the extra dimensions that leads to a new set of constants and a new universe. Of course, this is just one possibility. There are many other theories that attempt to explain the origin and nature of the constants of physics, but they all share a common thread: the idea that our universe is not unique, that there are other possibilities out there, waiting to be explored, and perhaps even created. Here's what's wild. If vacuum decay is possible, then it might also be possible to induce it, to deliberately trigger the creation of a new universe. This is, of course, a highly speculative idea, but some physicists have considered the possibility of creating a vacuum decay bomb, a device that could generate a tiny black hole and trigger a vacuum decay event. The ethical implications of such a device are staggering. It would be the ultimate weapon of mass destruction, capable of wiping out not just our planet, but our entire universe. But it could also be a tool for creation, a way to seed new universes and explore the vast landscape of possibilities that lies beyond our own. Now, before you start picturing mad scientists in underground layers, it's important to emphasize that this is all highly theoretical. We don't even know if vacuum decay is actually possible, let alone whether we could control it. But the fact that we're even contemplating such possibilities speaks to the power of human curiosity and our relentless desire to understand the universe and our place within it. We're pushing the boundaries of knowledge, venturing into uncharted territory where the stakes are higher than ever before. The analysis continues. Scientists began to look at the actual numbers within the models themselves. How far can we really push our understanding? The analysis continued. Scientists began to look at the actual numbers within the models themselves, scrutinizing the constants, the variables, the predicted outcomes against the observed data. And that's where things got complicated. See, even if we accept the possibility of vacuum decay, the numbers just don't quite line up. The energy scales involved are so incredibly vast, the probabilities so infinitesimally small that it becomes difficult to reconcile the theoretical framework with what we actually observe in the universe. The models suggest that the universe should have already decayed, that we shouldn't be here. And yet, here we are. It's a bit like trying to fit a square peg into a round hole. You can force it, you can fudge it, but it never quite sits right. And that nagging sense of unease, that persistent feeling that something is missing, is what drives scientists to keep searching, to keep questioning, to keep pushing the boundaries of knowledge. This isn't just about abstract physics. It's about our place in the cosmos. If the universe is inherently unstable, if our existence is predicated on a knife-edge balance of fundamental constants, then what does that say about our significance? Are we merely a fleeting anomaly, a cosmic accident destined to be swept away by the inexorable tide of vacuum decay? Or is there something more? Consider the possibility that our understanding of vacuum decay is incomplete, that there are factors we haven't yet accounted for, forces we haven't yet detected, principles we haven't yet grasped. Perhaps there's a hidden mechanism that stabilizes the vacuum, preventing it from decaying even when the conditions seem ripe. Perhaps there's a connection between vacuum decay and other fundamental phenomena, such as dark energy or dark matter, that we're only beginning to understand. Or perhaps, and this is where things get really interesting, perhaps the very act of observation plays a role in preventing vacuum decay. It's a controversial idea, one that touches on the deepest mysteries of quantum mechanics, but it's not entirely without merit. The quantum world is famously weird. Particles can exist in multiple states at once. Superposition and entanglement defy classical intuition, and the act of measurement can fundamentally alter the system being observed. Is it possible that the universe itself is a quantum system, and that our observations, our attempts to understand it, somehow influence its stability? It's a mind-bending thought, but it's one that some physicists are taking seriously. They're exploring the possibility that consciousness, or at least some form of information processing, is a fundamental aspect of reality, and that it plays a role in shaping the universe we inhabit. Now, I know what you're thinking. This sounds like science fiction. And, to be fair, it does push the boundaries of what we currently know. But it's important to remember that science is a process of exploration, of venturing into the unknown, of grappling with ideas that may seem outlandish at first, but that ultimately lead to a deeper understanding of the world. And that's where CERN comes back into the picture. CERN isn't just a particle accelerator, it's a window into the fundamental building blocks of reality. It's a tool that allows us to probe the deepest mysteries of the universe, to test our theories, to challenge our assumptions, and to uncover new phenomena that we never could have imagined. The LHC in particular is pushing the boundaries of what's possible. It's colliding particles at energies never before achieved, creating conditions that haven't existed since the earliest moments of the universe. And in doing so, it's giving us a glimpse into the realm where vacuum decay might actually be possible, where we can potentially observe the seeds of a new universe being born. Of course, the risks are immense. Tampering with the fabric of reality is not something to be taken lightly, but the potential rewards are even greater. A deeper understanding of vacuum decay could unlock the secrets of the universe, allowing us to manipulate the fundamental constants of physics, to create new materials with unprecedented properties, to develop technologies that seem like science fiction today. It could even allow us to create new universes, to seed the cosmos with life and intelligence, to expand the boundaries of existence beyond anything we can currently imagine. But before we get there, we need to address the fundamental questions that still plague us. We need to refine our models to gather more data, to develop new theoretical frameworks that can reconcile the observed stability of the universe with the theoretical possibility of vacuum decay. This will require a collaborative effort, a global partnership of scientists, engineers, and thinkers working together to push the boundaries of knowledge. It will require a willingness to challenge our assumptions, to embrace new ideas, and to venture into the unknown even when the path ahead is uncertain. And ultimately, it will require a deep sense of humility, an awareness of the limits of our understanding, and a recognition that the universe is far more complex and mysterious than we can ever fully comprehend. The search continues, and the answers may be closer than we think. If you're interested in supporting more science-based explorations, consider subscribing.